Meta-regression is a statistical technique used in meta-analysis to explore the relationship between study-level characteristics, such as study characteristics, participant demographics, or intervention features, and the effect sizes observed in individual studies. Subgroup analysis is a specific type of meta-regression. For instance, a subgroup analysis can reveal whether certain groups respond differently to an intervention. Even if a forest plot shows that an intervention is not effective across all studies, a subgroup analysis might demonstrate that a specific age group of patients does respond positively to that intervention. To perform meta-regression, the first step is to create the corresponding data_regression_outcome.csv files for each outcome by clicking the buttons in step 8.1. Once you check your directory, you should see these new files added. Open these files to enter your covariates. You can input two types of covariates. For example, in covariate 1, you could group the studies based on the age of the patients. Here, I'll label the age groups as age 1, age 2, and age 3. For covariate 2, I'll group the studies based on the sex of the patients, labeling males as 1 and females as 2. Once you've completed this data entry, save the files and proceed to the other files. Once all are ready, refresh the app. In step 8.3, you'll need to select the meta-regression method. Meta-IMU offers various methods for meta-regression, but explaining the differences is beyond the scope of this video. If you're interested, please refer to reference 1 for more information. In this demonstration, I'll choose REML for all outcomes, which is also the default method. Now, let's go through the output you can see here. The first line indicates that a mixed effects model has been fitted to the data, just as intended. The following lines provide details on the amount of heterogeneity explained by the model. We see that the estimate of the residual heterogeneity variance, which is the variance not explained by the predictor, is tau squared. Next, we have an I-squared equivalent indicating that, after including the predictor, the percentage of the variability in our data can be attributed to remaining between study heterogeneity. The last line shows the R-squared value. This shows the percentage of the differences in true effect sizes can be explained by our subgroup, which is age. Moving on to the test of moderators, if the p-value is less than 0.05, this indicates whether our predictor, the age, does indeed influence the effect sizes of the studies. In the final section, we find details on the estimated regression coefficients. The first row shows the intercept, which is the expected effect size when our predictor is 0. The coefficient we focus on is in the second row, where we see that the model's estimate for the regression weight for age. This means that for every age group, we expect the effect size of a study to increase by this amount. If you wish to learn more about the interpretation of the meta-regression results, please consult reference 2. The bubble plot displays the estimated regression slope alongside the effect size of each study. The size of the bubbles varies, with larger bubbles representing a higher weight. Meta-IMU provides meta-regression analysis and bubble plots for covariate 1, covariate 2, and for both covariates combined. The interpretation of these plots is the same as I've just described. Finally, in step 8.4, you should have a forest plot with subgroup analysis ready. You can refer back to reference 1 in step 6 to interpret those results. If you notice that some parts of your forest plot are truncated, as we see in outcome 1, simply go to the side panel and adjust the slider. Increasing the height of the forest plot will allow the full image to be displayed properly.